So welcome, and thanks for joining us, and thanks for attending our session here on DHCP, now DNS Security. Same thing really, close enough. So the session today is around DNS Security and how you use it and how we think about DNS Security as a product functionality. And we split up the session into 4 parts. The first, you have to listen to me, to my German accent. It's beautiful, it's awesome. And I will talk a little bit about what drove the introduction of this product, why do we think we need to address DNS as a threat vector, how we think about it from a product management perspective. And then the second part, Brian Lee from Unit 42 will walk us through how adversaries use DNS specifically for DNS tunneling to bypass network security devices. The third part, Daiping Liu is joining us from our threat research team. He has been working on a lot of the machine learning algorithms we use to identify all sorts of malicious domains. And then I'll be back on stage to talk about how to best use DNS security, and more importantly, how to deploy automated actions. That's a hot topic for me. So to start off, first, when in product management, we always like to think of what is the problem we're trying to solve, and really making sure we understand this problem as best as possible. So one thing that's pretty obvious is DNS is required on every network right now, right? I mean, it's one of the pillars of the internet. Without DNS, the internet wouldn't really work well for users because it does one function: translate human readable names into machine usable network addresses. So every firewall has a rule that says allow port 53 UDP, hopefully not. Hopefully use app ID for that purpose and you just allow DNS. But every firewall has a hole punched in for DNS, right? At the same time though, not a lot of companies have good visibility into DNS. A lot of companies don't even log DNS requests in their local DNS resolvers. And if they do so, there's so much DNS traffic that most of these logs roll over after 24 hours, and you don't really have a good handle on it anymore because you can't really look back like what triggered something, what events are really interesting, etc. Just out of curiosity, in this room, who's logging DNS traffic? Okay, that's actually a lot less people than I thought. And who is actually evaluating or using that information in the SIM for research purposes? Okay, that's also not a whole lot, but more than in the previous session, so that's good. And because of that, because a lot of customers just, we have to allow it, a lot of customers don't have good visibility into it, adversaries use DNS for their own purposes, and that is usually used for command and control. And what we're talking about in this case is relatively simple: either resolve the command and control infrastructure through a static domain, through DGA-generated domain, we'll talk about that more, or use it to bypass security controls altogether. So we did a little bit more research, and we looked at some of the wildfire, or all the wildfire samples that we've seen over the years, and tried to figure out how many of those do use DNS at some stage in the attack, really. And it turns out 80% of the malware we've seen uses DNS, either, again, to resolve the command and control infrastructure through automated means, through DGAs or hard-coded domains, but also, as I said, like DNS tunneling to bypass DNS controls altogether. What is interesting is that the rate of new malicious domains that pop up that we observe, it's honestly, it's mind-blowing. So right now, in our databases, excluding DGAs, we know of at least 36 million malicious domains, or domains that are used for malicious purposes. So that number by itself just gives you a sense of what scale is really needed to provide meaningful security service around it. All right, and then Brian will talk about DNS tunneling a little bit more. Specifically, one of the threat actors we see there is called OilRig. It's one of his pet projects. So we'll talk us through how that works. So the other thing that we looked at is, why do the current approaches that are available to our customers not really work well? And there's a couple of areas where we are guilty as well, right? I mean, we used to just provide a static list of known bad domains to the firewall. And the problem at that point is the firewall only has so and so much memory, or any network security device only has so and so much memory. So you have to choose which domains you want to add until you reach the capacity of that device. In addition to that, to make it worse, we have to rely on customers or users or like the admins of the firewall really to download these lists periodically, put them in effect on the firewall, commit that config that includes these lists so that they can be effective. Now, from us identifying a malicious domain to that domain being blocked on the firewall, it could take hours, it could even be days, which means that's all time an adversary has to roam freely through your network because the command and control channel can be established. What it also doesn't address is domain generation algorithms, or DNS tunneling, because it doesn't help us dynamically identify malicious domains we have never seen before. So we need to have some analytics behind it to really identify these malicious domains as they pop up. And my personal favorite, if you try to manually respond to a threat that is highly automated, good luck with that. When an endpoint is exploited, the adversary establishes a foothold on the system, establishes persistence, downloads additional payloads, etc. All of that is automated. If you're trying to manually respond to that, I mean, if you can pull that off, then more power to you, but most people can't. So we need to have a means to automatically respond to those threats. So what we did is we came up with this thing called DNS Security Service, which is a cloud-based service, very similar to PANDB in its architecture. Just out of curiosity, who in this room is using PANDB, URL filtering in Palo Alto? Good, okay. For those of you who haven't raised your hand, you should look into that. It's a really cool service as well. So it's a cloud-based service, and what we can do with that is, first of all, we can provide all of the information we have available in our databases through our research to all of our customers, and we can update that in real time. So I want to walk through a couple of the data sources we use for that purpose. So we have, first of all, passive DNS, which is passive DNS information we collect through partners. We also collect those through customer firewalls. If you opted into that, you share that information with us. If you do so, thank you very much. That's awesome. It's really helpful because
via telemetry or via the sinkhole, or how do you guys get it from customers?
It's via telemetry. Yeah. And that information is really helpful for us because it gives us a good lay of the land. And it also tells us, which is really interesting, I think, what DNS resolution you see locally versus what we would see when we try to access a site, because those don't necessarily match up. Wildfire, of course, is a great source of all of that information. Every sample we analyze with Wildfire, if we identify command and control, we'll add these domains as well to the service. URL filtering, of course, malicious websites that we identify are added to the service if they're domain-based. If it's URL-based, it's a little bit tricky, of course. We have industry sharing, or like intelligence sharing with industry peers through the Cyber Threat Alliance. And then, of course, our Unit 42 research team also provides us information there. One thing that we don't really talk a lot about, or haven't done so far, is a honeynet project. So a couple of years ago, some of our researchers put up a honeynet to analyze and research really IoT malware. So we detected a lot of malicious domains through that, specifically targeting IoT devices. So all that information also flows into this new service. And again, update in real time. Now, on top of that, we also added a bunch of interesting machine learning algorithms to automatically and inline detect domain generation algorithms, for example, or detect DNS tunneling domains and make that information quickly available to our customers. And all of that flows into the device or is accessible to the device. So the device at that point doesn't really hold a list anymore. It's really just a cache of the verdicts that it receives as it sees network traffic. Okay? So what does it really do? It helps us to achieve really three things. One, we can provide all that information we have, and we can, me personally, I don't like the term predict, but we can in real time identify malicious domains as we see them, even if we have never seen them before. But as we see them, we can identify them. We have a solid response to domain generation algorithms of all sorts, and we'll talk more about how we detect those. And then, of course, we can automate our countermeasures as we see the signal, as we see these IOCs on the network. And now we'll talk about that a little bit more. But next up is Brian, and he's going to talk about how adversaries use DNS, specifically DNS tunneling.
All right, thanks, Martin. Hey, I'm Brian, and I'm just going to spend a little bit of time now chatting about why we're even doing this. So basically, presenting from the adversary perspective, why are we taking so much effort to actually try to secure DNS abuse? So the primary thing really for adversaries why they use DNS is one of two things and a little bit of the third. So one thing is generally just convenience. Much like any other internet citizen in the world, nobody wants to use direct IP connections if they don't have to. It's like remembering a ton of phone numbers, much like how we don't use phone numbers anymore. We just have address books in our phone that has everybody's names in it. They like to use domains too. It's much easier to remember, it's much easier to spin up, and not to mention with the prevalence of VPS providers nowadays, now you have an ephemeral IP and an ephemeral domain, both of which you can spin up and take down as fast as anybody else. So, knowing that second portion of why they may also use domain names for basically everything they use, everything from delivery, exploitation, command and control, etc., is that it also is pretty easy to hide within the noise. So if any of you have actually hooked up, say, a Windows 10 system to your network and just started looking at all the DNS lookups it does, it is crazy how many DNS lookups it just initially, right off the bat, starts performing to everything from Microsoft-based servers to random CDNs that you're like, are these actually legitimate? So it just starts scrolling by, and that's with any other OS really. And once you start scaling this out to thousands or hundreds of thousands of systems that you now have on your network, the amount of DNS lookups is just monumental, which is probably one of the reasons why not a lot of people are actively inspecting and collecting all that traffic. It's just too much. So the adversaries know this. They know that if they just register a domain that looks vaguely similar to a real domain, so instead of Microsoft.com, they do Microsoft with a couple zeros in there. For a human eye, you're basically not going to be able to tell. There's just too much data in there. Now, for a machine, that may become a little easier, but a machine can't inherently just tell you if it's malicious or not either. It can tell you it's anomalous. It can tell you it's slightly different, which is why we need a lot of that additional analytics to actually try to provide that specific verdict. So with all that said of DNS abuse, that last portion, it brings us to DNS tunneling. So in addition to just being able to use domain names as they were designed, but in a malicious manner, they can also use this thing called DNS tunneling. So the concept of DNS tunneling is not new at all. It's been around for decades, really. There was a white paper written decades ago basically detailing how one could transfer actual data through DNS rather than just using it for DNS lookups. And if we really think about it, it's just like any other network protocol, right? It is actually just transferring data back and forth. It's just it was designed to only transfer very little amounts of data. So for example, if you're using A records, it's 4 bytes at a time that's coming back. That's really, really little. If we're using IPv6, and we're talking about for a quad A record, 16 bytes every single time. So we're talking it's even slower than your old 14.4 dial-up modem here. But if you're an adversary, you kind of have time, right? Your average breach takes like 6 months to detect in the first place, so you can sort of chill there and start transferring some files back and forth over DNS. And because there's so much DNS lookups going on inside your logs, you may not necessarily be seeing it. Especially if you're not even inspecting your logs, you're definitely not going to be seeing it because you just have some random machines that's just doing tons of DNS lookups, which is just normal behavior for, say, a Windows 10 system. So let's talk a little bit more about how DNS tunneling actually works. So this is not a comprehensive diagram. Comprehensive diagram of how DNS tunneling works, or even how DNS works, but it's simplified. It gets us there. So essentially, what happens is you have a system that gets infected, right? And this infection, it's probably going to be a phishing attack because everybody loves clicking on stuff. I like clicking on stuff. You like clicking on stuff. Our users like clicking on stuff. And if it's not clicking, it's tapping or it's swiping. You know, we just like interacting with our systems, and we've been very conditioned to just look at links, images, whatever, and just immediately start poking at it, especially with all of our smart devices. So we get that phishing attack, we get infected, and now our backdoor is starting to do its command and control. So right off the bat, it does the DNS lookups, assuming that we're using DNS tunneling here. Now your local resolver doesn't know this domain, never seen it before. So it forwards that DNS lookup off to the root server. Now the root server says, okay, I've seen this, and this is the authoritative DNS server, which just happens to be owned by the adversary. Now that request gets forwarded back out. The adversary server now has some custom software on there, the command control handler, to take that DNS lookup and then craft a proper response to it, which is very much custom and could be data transfer back. It could be just a hello. It could be a pong, whatever it is. And now we've established that channel, and then we can just do continuous lookups. So we think about this, though. We're talking about 4 to 16 bytes per request coming back down. I mean, you can imagine if you're trying to, let's say, transfer a file back into that infected host, let's say it's something like Mimikatz, which is approximately 500 kilobytes or so, that's a lot of lookups, right? That's a lot of lookups in response that are coming back and forth. So you'd imagine if you're actually inspecting this, it should be trivial to actually look at, to detect this stuff because of the amount of volume there. But again, unless we're actually looking at this stuff, we're never going to find it. We have to know that to actually look for this stuff to actually detect it. Okay, so with all that said, I went backwards. Nope. Buttons are hard. Okay. I was clicking on all the buttons here because I just like all of them. So that brings us to our favorite group, Oil Rig. So it is my pet project because I named it. Oil Rig. Me and my reverser, Rob Falcone, spent 2 days trying to name this adversary group, and we came up with Oil Rig. If you saw the list of names that were vetoed or rejected simply because they were either offensive or too hard to say, you would just, it's really funny. I've actually saved that chat log now. But we talk about Oil Rig so much because we did expose it, and we've been tracking it for a number of years now. But this group is actually kind of fading away, or has actually completely ceased by now because of several tweets that were sent out. So back in March or so, this so-called whistleblower started tweeting that they have all this data about Oil Rig. They want to expose what they were doing on the offensive side. So this is actually a really rare opportunity. We rarely ever get to actually get the source code for tools that adversaries are using, to get all the credentials that they've dumped, the targeting of various organizations that they've performed, the web shells that they've deployed, basically had all of that dumped onto the internet. Now, if you're the adversary, you're like, well, that sucks. We're going to have to shut our doors because that's just everything we've had. So ever since then, their activity's pretty much gone to zero, but we had that rare opportunity to actually look through all of that data and basically validate that we've been doing our research properly. It's always a good feeling when you actually look at the real data and then look at the data that you've collected, compare them, realize you are on the right track. That was a good win. But unfortunately, because now their activity's gone, I can't really keep on poking that golden goose anymore. So the reason we're talking about Oil Rig now, though, is because over the course of the 3 years or so that we were tracking them, they were one of the only adversaries to consistently use DNS tunneling techniques in all of their backdoors. So they probably used about a dozen or so different backdoors over that time frame, and almost every single one of them had some amount of DNS tunneling capability in there. So that's not really a common technique you see in a lot of other adversaries. So the fact that this specific group decided that this was the way they want to use their command and control channel was actually really unique. Also, because we kept on seeing it over the years, kind of also told us that it's highly successful. For every single adversary out there, if their technique isn't working anymore, they generally will move on to something else because they need to complete their mission, right? So the fact that they kept on using it over and over and over the course of 3 years tells us that nobody was inspecting their DNS traffic, and all of these organizations were getting compromised. So if we were to unpack one of their attacks, their attack campaign, this was an attack campaign using a piece of malware called Bond Updater. We named it Bond Updater because there was a string inside that said Bond Updater. So we're like, okay, that's cool. That's obviously what it's named. Turns out, based on the data dump, it's actually called Glimpse, which is a way cooler name than Bond Updater because it actually makes sense, right? Glimpse with the eyeball. It even had an eyeball icon. So basically looking into those victim systems. So we should really just call it Glimpse by now, but we've written blogs that say the Bond Updater, so we have to stick with it. So if we go across the attack lifecycle here, we have that initial delivery. So these campaigns were using phishing attacks that had malicious Excel documents attached to it with a malicious macro embedded inside it. Once you ran that macro, it installed this backdoor Bond Updater, which is a PowerShell script. So it was fileless. I hate using that term because there is still a file. There's a script file, but it does construct a backdoor using PowerShell commands. once it does that, it establishes persistence via a scheduled task. So this is not fancy at all, right? I mean, we can all think of various ways you can establish persistence on a system, but they just use straight up scheduled tasks. Just set a new hidden scheduled task in there. Every 2 seconds, it will just continuously run the script. Once it starts doing that, it starts beaconing out. And this one uses quad A records, so it has that 16-byte IPv6 response. So once it starts beaconing out, and then that command control handler on the opposite side can then start running commands. They can download files, upload files. They essentially have full control over your system using DNS tunneling. And all you will see is just tons of DNS lookups and responses. So to actually visualize this, I created a demo video. Now, the first time I gave this, it failed. For those of you that were in my session or in our session on Tuesday, you would see that my video didn't work, and I had to use hand puppets to actually demonstrate this. So we're going to hope that this one actually works. Okay, I have a black screen again. It works. Okay. Whoops. Go back. I think I already broke it. I actually may have broken my demo again. Okay, back here. Okay. I want to pause it. Nope. Okay. We're just going to let it play because apparently I do not have the ability to pause this video. Play. I may have. God, buttons are hard, man. Telling you. Okay, we're just going to play through this video. So this is the Bond Updater demo. Essentially set up a server system. It's running Node.js with a .NET front end called Glimpse. We have a victim host. There's some interesting files on there. This one says the contents of this file are really important. So we get the email. We have the document. The user opens it because, again, buttons and clicking is fun. It's a bunch of gibberish, but screw it. I just want to hit enable macros because, yeah, why not? So if we're running Wireshark on the system, this is what happens right off the bat. You just get tons of lookups. On our server system, it's just scrolling by telling us that it's sending all this data back. And right off the bat, we have that system that checked in. And this specific backdoor will run a whoami and ipconfig as the default command. So I already have all that data streaming back into my command control handler. From there, I can basically decide what else do I want to do. If we look at those tabs, we have a command, upload, and download, and we can basically run through that. What we just did was run a command, and again on the victim host, we see a whole bunch of DNS lookups happening. We see the response, and it dumps the file back down. We actually just downloaded files. So we downloaded that important file back down to our server. Now we're going to actually upload a file, so we're going to put some additional post-exploitation tools onto the victim. So we're going to go ahead and upload that, and it's just going to start scrolling by on our server system again. If we look at our victim, again, just tons and tons of DNS lookups scrolling by. I actually just truncated that because that took about 10 minutes because it was just, it's, again, 4 bytes or 16 bytes at a time. I think that one's using text ones, but that one was also limited to something like, I think it was 100 bytes per lookup or for response. And if we actually look at that victim system and we look at the directory where files are dumped, this file does exist. We go rename it if we wanted to, and we look at the property of that file, and it is the actual file that we just uploaded there, all via DNS tunneling. So if you're doing HTTP inspection, if you're looking at your snort logs and you don't necessarily look at DNS, you're going to miss all of this stuff. But if you were actually looking at your DNS logs, you would all of a sudden just see a ton of random DNS lookups using weird subdomain names. So they like to use the first label specifically, the oil rig group. Each label in a DNS lookup in a host name is limited to 63 bytes. For those guys, they had hard-coded characters in there as well, so they could actually only transfer 60 bytes at a time going outbound. So again, just really, really little amount of data. It's all chunked up. It's extremely voluminous, but you have to know to actually look for it. Okay, so next up we have DiePing to actually explain how are we actually doing all this from a technology side.
Okay, good morning. I'm DiePing, and I'm a security researcher at Palo Networks. Oh, yeah, sorry. So, thanks for the great introduction of DNS threats by Brian. So you've known that DNS has a lot of security problems. Now let's have a look at how we at Palo Alto Networks to address these security problems. So we believe that most DNS security problems must be addressed in real time. Unfortunately, most existing DNS security solutions cannot provide real-time protection. For example, most DJ detectors are designed for the offline forensic analysis. However, DJ domains are usually for only once, and thus a postmortem detection cannot provide sufficient protection. So one of the main features that make our DNS security service stand out is real-time protection. So now let's have a look at how our DNS security service works to provide real-time protection. So when a DNS query is sent out from an end host, the DNS query will be intercepted by the firewall. And the firewall first checks with the local cache. And if the query domain is not in the local cache, the firewall will forward the DNS query to the DNS servers and our DNS security service in the cloud. And then our DNS security service will return a verdict indicating if the domain is malicious or not to the firewall before the DNS server returns response. So when the firewall receives the response, it already knows that if the domain is malicious or not. And if the domain is malicious, if the domain is malicious, the DNS response can be dropped. Otherwise, the firewall can let the response go through. So given the potential infinite scalability of the cloud, our DNS security service can provide many different protections. But in this talk, I will focus on the two that use machine learning a lot. And one is real-time DJ detection, and the other is real-time DNS tunneling detection. So the first is DJ detection. So to explain the basic idea of our DJ detector, let's have a look at the typical names of DJ and non-DJ domains. So we can see that non-DJ domains, they usually use meaningful words in their domain names. Anyway, the main purpose of domain names is to help people to remember the domains. And meaningful words can help people to remember. So however, for DJ domains, they usually use random characters. This is mainly because attackers need to generate a large number of DJ domains to bypass the blacklists. And attackers don't want to use the domains that can be possibly be registered by others so that they can register any of the DJ domains for command and control when they want. So in summary, DJ and non-DJ domains, they usually have different probability distributions of characters. So we use the Markov chain to model the characters in domain names. So in Markov chain, the nodes are the characters that are allowed in domain names. And the arrows denote the probability that a character is followed by another one for DJ and non-DJ domains respectively. So with Markov chain, we can evaluate how similar a domain looks like DJ. But a domain looks like DJ does not mean that it's actually DJ. For example, these two cases. They look like DJ, but actually they're not. So that means Markov chain can cause false positives. So in order to address the false positives by Markov chain, we use the other two intrinsic properties of DJ domains. First, DJ malware needs to constantly connect to a large number of automatically generated domains that are not registered yet. So that means most of these DJ domains are never successfully resolved. So by successfully resolved, I mean a valid IP address is returned for the domain. So from the left figure, we can see that actually over 90% of DJ domains are never successfully resolved. However, for the benign domains, about 80% are successfully resolved for over 1,000 times. So our second insight is that even when a DJ domain can be successfully resolved, they are usually used within a short interval, for example, within 1 year or even within several days. So, however, for the benign domains, we can see that actually they are usually used more than 1 year. So combining the Markov chain model and the domain history data, our system can effectively detect DJ domains in real time with a few false positives. When a DJ domain is detected, we also want to know if the DJ domain belongs to a known family. So to achieve this, we find that most DJ families, they usually have unique patterns in their domain names. For example, they can use different top-level top-level domains like .com, .net, and various country codes. And they can have different uses of special characters like hyphen minors and digits. Based on these patterns, we use the machine learning algorithm random forest for the multi-class classification. So given a DJ domain, the random forest can output the probability that this domain belongs to a specific DJ family. Okay, now the DNS tunneling. So from Brian's talk, we've known that DNS tunneling encodes messages in subdomain names and transmit to the attackers. And attackers receive this message at the authoritative DNS servers of the domains. So now let's have a look at the characteristics of the authoritative DNS servers of tunneling and non-tunneling domains. So actually, we find that about 98% of non-tunneling domains, they usually use third-party managed authoritative DNS servers. And most of these authoritative DNS servers can actually be trusted because they are operated by Google, Amazon, or GoDaddy. However, for DNS tunneling, they usually they have to fully control the authoritative DNS servers so that they can receive the messages. So the DNS tunneling domains, they usually use self-hosted authoritative DNS servers. And there are also characteristics in the domain names of DNS tunneling. So for non-tunneling domains, they usually use meaningful words in the subdomain names. However, for DNS tunneling domains, they usually use random characters because these subdomain names are basically the encoded messages. And DNS tunneling also has several other characteristics. For example, since most of the subdomain names are encoded messages, they are usually queried only once, and there can be a large number of unique subdomain names on the same root domain. So all in all, DNS tunneling usually has a distinguished characteristics from normal DNS traffic. So actually, DNS tunneling can be detected as anomalies from the normal DNS traffic. So based on the above characteristics, we build the behavioral profile of DNS traffic for normal DNS for the benign domains. And then we detect DNS tunneling by identifying the domains with anomalous traffic. So this figure shows the anomaly score of tunneling and non-tunneling domains. So we can see that all of the tunneling domains, they have a anomaly score larger than 6.8. However, 99% of non-tunneling domains, they have a anomaly score smaller than 6.8. So although the anomaly-based detector can handle the unknown DNS tunneling traffic, it usually requires to accumulate several DNS queries before detection. But we want to detect the known DNS tunneling campaigns faster. For example, even with a single DNS query. So we implement the similarity-based DNS tunneling detector, which has two components. So the first component looks for the patterns in the domain names. So we find that some of the DNS tunneling malware and tools, they usually have encoded, hard-coded information in the messages. And also, although attackers can use many different domains for DNS tunneling, they usually share the same infrastructure. For example, they can use the same authoritative DNS server, especially in terms of IP address. So now let's have a look at the architecture of our DNS tunneling detector. So when a DNS query is received, the DNS query will be dispatched to the anomaly-based detector and the similarity-based detector simultaneously. So the query is the DNS query is detected to be DNS tunneling, as long as one of the two detectors considered to be tunneling. And when we detect some new tunneling campaigns by the anomaly-based detector, we extract the patterns and feed the patterns to the similarity-based detector. So in summary, so with the anomaly-based detector and the similarity-based detector, they can complement each other for comprehensive and fast detection of DNS tunneling. So that's all my part. Thanks very much, and I hand over to Martin.
All right, thank you. So I want to talk about how you actually can use these detection capabilities to prevent adversaries from using DNS for their purposes. So first of all, just to get a sense, show of hands, if you know what DNS sinkholing is. Okay? And are you also using it? A few? Okay, good. So for the other folks who don't know it yet, so just to recap really quick, if we have a network with an internal DNS resolver and we see a client performing a DNS lookup to a potentially malicious domain or like a command and control domain, if we would just base our verdict and our decision off of that source IP address for that DNS lookup, we would essentially start blocking the DNS server all day long. And that's obviously not something we want to do. If you block DNS, if you break DNS, fun things can happen on the network. Phones turn hot and people call and yell and scream at you, so you don't want to do that. So what we do is, when we see this request, we essentially intercept it on the firewall and provide a bogus response back to the endpoint. Bogus because we use a bogus IP address to lure that client into connecting to that IP, so we can then, through the TCP connection, identify the client that is actually infected, is actually trying to establish command and control to his command and control domain. Does that make sense? So by default, we use this IP address, 72.565.111, which is a single IP address in the Palo Alto Network's IP space. So we are collecting some data from that. We want to see, if we can, what type of malware is calling out. We use it for research purposes. So usually like there's not a whole lot of data that's being exchanged. It's usually like the first connection that is established where we create PCAPs from to see, is this malware we've seen before, and how does it behave? But you can also, of course, use your own single IP address and configure that in the firewall accordingly. All right, so how do you use that information? How do you use that connection, that signal? So I provided a little bit of a high-level policy here, so you got to read that from the bottom up. So here on the bottom, you have your local policies. Those are your own security policies that you set up, right? And all of these security policies have an anti-spyware profile attached with a single IP address configured, or with sinkholing configured. Then what happens is you have another rule here, rule 3, that blocks access or allows access, depending how you want to set it up, to the sinkhole address, the sinkhole IP address. But what is important here is we want to make sure we log this event, and then we assign a log tagging action in like the log profiles to that rule. Does that make sense? So in this log tagging action, what we do is we tag the source IP address of that connection request and add that source IP address to a dynamic address group. Now, this dynamic address group allows you to treat these clients differently. And why is this important? So first of all, of course, you want to have a rule 2 that says block all access for these guys, and then allow them restricted access. Reason for that is relatively simple. You want to block any sort of download of secondary stage payloads, right? Like PowerShell scripts, like executables, right? Whatever the case may be. You also want to make sure that these clients cannot access your data center anymore, potentially. Or you make it harder for these clients to access your data center by employing multi-factor authentication, for example. Right? You can, if you have a client you believe it's infected, you could say, hey, access to the data center, for example, RDP services, anything that could be an administrative service, I require multi-factor authentication. You still want to allow some download of executables. So for example, in conjunction with app ID, you could say, if you want to download an executable file, this endpoint, then it's only for the app MS update, and it's only executable from that source because that would be a Windows update to patch potential security holes. But this is the idea around how you can automate your countermeasures. You can restrict access to these endpoints if you see any indicators of an infection. What has changed in 9.0, in PanOS 9.0, which is really cool and important for this functionality, is around dynamic address groups. So dynamic address groups, first of all, have much higher capacity, and hopefully you don't need higher capacity if you want to isolate hosts. I hope you don't have that many infected hosts on your network. But the other thing is the updates to dynamic address groups now take like 1 to 2 seconds. So it's super quick. So as soon as we see some indicator of compromise, we can use that information to right then isolate that endpoint. And my favorite functionality that we added is you can have an expiration time, which means you can add an IP address to this dynamic address group, and you can make that expire, which ultimately does one thing that is super important here. If you see continued command and control attempts, continued malicious activity, that would keep that host in this dynamic address group, and these restricted rules would still be applied. However, if we don't see that anymore, for example, a user accidentally pinged a command and control domain or clicked on a link he was not supposed to click on, that user or that endpoint will fall out of that dynamic address group because that IP tag will expire unless we see, of course, additional malicious activity, and everything goes back to normal. So very, very important functionality we added there. So what does this really mean? We want to bring it back to the oil rig attack, to that campaign. So previously, when you look at the countermeasures we were able to deploy, sure, the initial exploitation of the endpoint, we could have detected a weaponized file. We have signatures to detect Office documents that contain macros. And that can also be used, by the way, for automation. Give you a good example. If you have a user who receives a document or downloads a document that has macros in it, it's a good idea to maybe prevent them for the next 5 to 10 minutes from downloading PowerShell scripts or executable files, etc., just to make it a lot harder for the adversary. And of course, you can log all file downloads. If you're using file blocking profiles, by the way, you should use them anyway, even if you don't block files, because you should set your policy to at least alert and establish that visibility. So you see all file transactions on your network. Really helpful, just as a side note. But then anything around DNS tunneling, really, we only had the opportunity to really look at app usage reports, see if there's any change from a volumetric perspective that could give us some hints. And that's really the big gap that DNS security completely fills. Anything around DNS, any malicious activity around DNS is addressed through DNS security, through this new service. Now, how does it fit in with the rest of the product portfolio? It's, as I said, a cloud-based service that we introduced. Very much like, or very similar to PanDB, to our URL filtering product. Threat prevention is, of course, one of those cloud-delivered functionalities. But what that also means is it doesn't just address the capacity issue. It also means that whenever we innovate and add new machine learning algorithms to detect new malicious domains or detect malicious domains a lot faster, you don't have to worry about it. All you need to have is PanOS 9.0. You need to have this functionality. You need to have DNS security. And all the innovation that we release over the next years, hopefully, you will absorb those automatically. You can take advantage of those automatically.
Does this show up in the threat log now in terms of any clients that are generating?
Yes, so the question was if this shows up in the threat log, and the answer is yes. However, DNS security does require a license, right? So you got to have that license and then enable it, and you're good to go.
And I heard yesterday in a different presentation, it's you have to have a threat license in order to use the DNS security.
That's a very good point. Yes, that's a very good point. So the comment was, you got to have a threat prevention license if you want to use DNS security. It's a very good point. And the reason for that is relatively simple. We don't believe that DNS security by itself is the silver bullet to command and control. It fills a gap, and it does a lot of good things to detect command and control, but there's still payload-based command and control, so we want to encourage our customers to use these two capabilities together. I'll give you an example. We have seen command and control that use Reddit. We have seen command and control that use Twitter. We can't sinkhole Twitter and Reddit, even though, I mean, we would like to, of course, but, but you get the idea, right? There's still payload-based detection that you need to have in place to really have meaningful command and control coverage. Another question? Was there another question? Yeah.
I've just noticed since uploading on my own test box the DNS signatures of the 902, if you go into the anti-spyware profile for this sort of thing, there's two different pre-built lists.
Correct.
Do you
Let me-
expect in both of those be set to sync
So let me talk about that. Yes. So when you go into the anti-spyware profile in 9.0, you see two options, two sources, right? There's a static list that we always had, 100,000 domains. That is part of threat prevention. That does not require DNS security. And that list is used now mostly for commodity malware, actual campaigns that are going on that have like widespread effect, right? So that list still works there. You don't need to use both. If you have DNS security, DNS security encompasses all of that. So you don't even need the local list anymore. But it doesn't harm to turn on syncing for both. Correct. Correct. The local content update list shows up with just threat prevention. DNS security service, the cloud service, that's the other option on top of that. Okay? Awesome.